Okay, so I think we can begin now, and this class will be recorded. So for those who are not able to join us today, so they can watch later from the saved videos. Okay, again, a very good morning to all of you. So are you doing good today? Have you all took your breakfast? Semua sudah makan ke? Okay, first of all, teacher would like to thank you very much for spending your time. So today we are going to discuss our next topic on 2.6, Bernoullis Principle. Okay. Okay, so does my screen still appear to you, students? Boleh nampak screen cikgu? Okay, so this is 2.6 Bernoullis Principle. So along this discussion, we can make it two ways communication. So you can ask any questions or you can type your response in the chat room. Okay. Okay, thank you. You, so we okay, boleh dengar sekarang? Boleh. Oh, kenapa sekejap tak boleh dengar, sekejap tak boleh dengar? Okay, tak apa. Okay, so we back to these two diagram. Can you guess the name of these two figures? Sorry for the technical error. Okay, Sinway, can you guess their name? Roberto Carlos, very good. Aiman, the second diagram is, the second figure is Roberto Carlos, a defender from Brazil. Yeah, very good. Faiz Subri, that one, he used to play with Penang Football Club. Okay, thank you, Aiman, for your response. Okay, this view situation you can relate to Bernoullis Principle. Okay, we have 1, 2, 3, 4, 5, and 6 situations here. So can you tell me what happened in the first situation? What happened to the paper when the man blow on top of it? Sinway. Parents, okay, can you respond to the first situation? What happened to the paper? You can see the paper is lifted, right? And the second situation when the man blow in between the two can. So yeah, the paper fly. We say the paper lift up, same way. Okay, what happened to both can when the man blew in between them? So you can see that the can became closer to one and another. Okay, then the third situation, the ping pong ball is placed closer to a water stream from the tap. You can see it is attached to the water. Dia melekat dekat air. And this is the fourth situation. Again, a man blow in between the two balloons. Again, you can see it come into context. Okay, so this is the situation given in your module. Okay, we have Boeing 747 there and an F1 car. Okay, there are two questions. How can the plane fly with a very heavy load? Second question, why can a Formula 1 car go through a sharp curve while traveling at 300 km per hour? So in these two situations, it can be related to Bernoullis Principle. Okay, so this is the everyday situation we can relate to Bernoullis Principle. Do you watch F1? Ada siapa tengok ke? Okay, or anybody used to be on board. Wei Shen, are you back to Malaysia yet? Sudah balik ke? Itu cuti lebih awal. Okay. Okay, let us go through the first learning standards to learn to describe the effect of fluid velocity on pressure. Okay, so this is what you have in your module on the very first page, and you can do it on your own. You can try it at home. You need to take a piece of paper. Kalau boleh ambil kertas, atau you can find any tissue or nearby, and you try to blow air above the paper or above the tissue. Okay, anyone would like to do the demonstration? You can open your camera and show to everyone. Okay, what happened to the paper when you blow air above it? Okay, any response? What happened to the paper as shown in this diagram? Student, malu lah. Sinway nak malu apa hari-hari jumpa dalam kelas. Okay, Nicholas pun malu. Tak perlu malu lah. Okay. So if you feel shy, okay, so you just type your response here. What do you think happened to the paper? It lifted upward. Very good. The paper is pushed upward. Oh, you can see the paper lifted. Okay, the paper lift upward. Lift itu upwards lah. Okay, so the paper lift. Okay, then which part of the paper has a lower pressure and which part of the paper has a higher pressure? Anyone? Okay, we have two parts. The first part is above the paper, second part below the paper. Muka tak pakai mask, tak boleh tengok. I am not wearing a mask now. Sekarang sudah tak wajib dah pakai mask. We have a new announcement made yesterday by our health minister. So tak pakai mask sekarang pun sudah okay. But for safety, we still put it on lah when you are in school. Okay, which one has a lower pressure or higher pressure, students? 5 arcade, 5 Baiduri, 5 Citrain. Lower pressure above or below? Higher pressure above or below? Okay, you can guess first, or if you are confident with your answer, you can type. Yang mana? Lower pressure. So lower pressure will be the top part of the paper. Meanwhile, the bottom part has a higher pressure. Okay, above low, yes, very good. And below or bottom has a higher pressure. Okay, later we will see why there are difference in pressure between the top and the bottom part of the paper. Okay, now which part of this paper does the air move at the high speed? So this is a very simple question. So you just check in which part you blow the air at. So that will be the part where the air moving with the high speed. Okay, so which part? Students, above. Okay, the clue is here, blow air above the paper. So the area where we blow the paper, so the air there moving with the high speed or high velocity. Yes, above, very good. Okay, now how to mark the direction of the net force acting on the paper. So where to draw the force acting on the paper, students? So from the first answer you can tell. Okay, since we know that the paper is pushed upwards, so definitely the net force is acting upward. Okay, so you draw an arrow showing the net force acting on the paper. Okay. So are you done with the first part? Okay, semua jawapan dia pendek-pendek saja. Alright, so can we go to the next slide? Okay. So now this is the second situation. You can take another paper. Okay, first one we need a single paper. So now we have a pair of paper. Dua keping kertas. Okay, hold two pieces of paper close to each other and blow steadily into the space between them. Okay, so if you are trying this at home now, okay, what happened to both papers, students? Okay, or you can guess what happened to the papers. So this one you can relate to the short animation I give you in the receipt situation earlier. So what happened to the papers when you blow the air between them? Anyone? Move toward each other, Nicholas say. Okay, so both paper attract to each other. They move closer to one and another. Okay, very good. Again, determine the region which has lower pressure and the region which has higher pressure. Okay, now, so for lower pressure, which part? In between or outside the paper? So we say low pressure is between the two papers. Okay, and outside it has higher pressure. Okay, thank you, Nicholas. And the next question, similar to the first one, which part of this paper does the air move at high speed? Definitely is the place where you blow the air at, okay, in between the two papers. So now how to draw the direction of net force acting on these two papers, student? Where to draw the arrow now to show the direction of net force acting? This is very simple. Since the paper is moved towards another, so the force are acting from both outside direction, from the left and on the right. Okay, so this red arrow showing the net force acting on the papers. Okay, so I think nothing more, nothing difficult yet. This is just the basic to understand Bernoullis principle. Okay, do you have any questions so far? Anything to ask? you can open your mic or you can type your question in the live chat. Okay, so let us go to the conclusion from these two simple activities. So what causes the movement of paper in both activities? Okay, this is due to resultant force. Okay, there is resultant force on net force acting, so it will cause the paper to move, okay, in the direction of the resultant force. Okay, how about the second question? How to explain the resultant force produced? What causes the resultant force to be produced, student? What is the reason? What produced the resultant force in this question? Okay, any idea? Explain how pressure gradient. Okay, why you always mention the word gradient? Actually, it is pressure difference. Difference in pressure, Nicholas. Okay, so this is how to explain in a complete sentences. The first one, we understand that the air move with the high speed at the blow region. So remember the region or the point where you blow air, the air there move with a high speed or high velocity. So it produces a low pressure region. Okay, there. So meanwhile, the region where the air moves slower has a high pressure. Okay, so this is the answer. The difference in pressure produces resultant force. Okay. So the keyword is here on the fourth point, difference in pressure. Okay, produces a resultant force. The first 3 points, how we explain. Okay, the higher pressure region and the lower pressure region is due to the speed of a moving air. Okay, high speed, low pressure. Low speed, high pressure. Okay, inversely proportional. So from here we can write the relationship between speed of air and pressure. So we say when the speed of moving air increases, so its pressure decreases. Or you can say it is inversely proportional. Higher air pressure and velocity. Higher pressure, low velocity, same way. Low pressure, high velocity. Okay, you get it now? So from these two activity, we can see that a speed of moving air is inversely proportional to its pressure, where when the speed increases, so its pressure decreases. Okay, student, you get the point from these two activity. What is the relationship between velocity and pressure of moving air? So we say they are, yes, inversely proportional. Okay. So are you done with this 1, 2, and 3? If you are done, you can type yes, so we can shift to the next slide. Okay, very good, Nicholas. How about the others? Are you done? I hope you are now sitting in the most comfortable way with your module in front of you, so you can copy or follow this lesson well. Sinway, no, okay. Okay, if you are done, just type yes at the chat room so we can move to the next slide. And later I'll show you the PDF copy for this module as well. So you don't have to worry about that if you miss any point. And later you can check back on this recorded video also. Okay. Okay, can we move to the next one, students? Okay. Thank you. Yes. Okay, next. Okay, so from this relationship between pressure and velocity of air, so we can come up with Bernoullis principle. Okay, anybody can say what stated in Bernoullis principle? You can check from your textbook on page 80 if I'm not mistaken. Yeah, page 80. So Bernoullis principle state that when the velocity of a fluid increases, so the pressure in the fluid decreases, and vice versa. Kafai give you an equation there. How to read that, Kafai? Okay. For SPM, we don't use this formula. This one is applied in a college or in a university level. So you don't have to worry, Nicholas. Kafai pandai, semua orang sini pandai. Okay. Tapi kita nanti tengok ada sedikit, ada a few question which involve calculation but only a simple one. We use P equal to FA only, or F equal to P divided A, the general formula for pressure. We are not going to use this formula as given by Kafai. Yes. Okay. So again, Bernoullis principle state that when the velocity of a fluid increases, so the pressure in the fluid decreases. So the key word is the blue wording. Okay, velocity of fluid increases, pressure in the fluid decreases. Okay, it's a very simple principle. So you can write this on the boxes provided in your module. Yes. Okay, are you done with the Bernoullis principle? The statement? Okay, so let us move to the next part. Okay, students, so that is to do with the first learning standard. Okay, to describe what is the relationship between pressure and velocity of moving air. Okay, so now let us move to the second learning standard to explain lift as a result of difference in pressure due to different velocity of fluid. Okay. Okay, so now this is our second activity. Okay, the aim is to study how fluid pressure is influenced by the speed of fluid. So in this figure, it shows you a venturi tube. So what is a venturi tube? It is a non-uniform tube. A non-uniform tube means it has a different diameter, okay, in certain part of the tube. Okay, so that is what we call a non-uniform tube. Another name is venturi tube. Okay, so this is the tube as shown in this diagram, and we have three columns: column P, column Q, and column R. And the water is flowing through this venturi tube. Follow this stream from X, it flows to Y, and then flows to Z. Okay. So the first question refer to X, Y, and Z. Can you arrange the speed of water in ascending order? Okay, can you try to arrange in which part the water flows the fastest and in which part the water flows at the lowest velocity or speed? Okay. Ascending order. Ascending order means from the lowest to the highest speed. Okay, which part it flow at the lowest speed? You can guess. Y is the quickest. Okay, and which one is the slowest? X and Z. So what is the arrangement? X, Z, Y said by Sinway. Okay, how about you? The others, what do you say? Arrange the speed in ascending order. So the first one is X, followed by Z, followed by Y. Okay, X less than Z, less than Y. Okay, or you can just write X dash Z dash Y. Macam tu pun boleh. Okay. You can arrange in this way: X, Z, and Y. Okay, as I type in the live chat. Okay, and refer to XYZ. Now arrange the pressure of the water in descending order. Okay, second question, the pressure in descending order. Descending order means from the highest pressure to the lowest pressure. Okay, the first one is speed. Second is the pressure. Descending order means from the highest pressure to the lowest pressure. Okay. Y, Z, X. Okay, this is yang mana ni, Nicholas? Is this the pressure? Okay, look at the question. Pressure from descending order. Descending order means from the highest to the lowest. Descending from the highest to the lowest. So macam mana? Sama lah. X, Z, and Y. Okay, first one is X, the highest pressure, followed by Z, and followed by 1, the lowest pressure. You just look at the first one. Okay, so it's just opposite. Okay, and mark the water level in the vertical tube P, Q, and R. Explain your answer for the lowest level. Okay, now when this water flow from X to Y and Z, so the water level will rises in each column P, Q, and R. But since they are non-uniform, so the water column will rises at a different level. So can you guess or can you try to draw the water level in each column? In which column the water level will rise up at the highest level? In which column the water will rise up at the lowest level, students? Actually, you can find the clue from the second situation when you look at the pressure. Okay. So highest pressure means it can push the water at the highest level. Lowest pressure, it push a little water only. Okay, rises to the column. So this is how we can draw. So at point Y, since the pressure there is the lowest, so only a small part of water can be pushed upward. Okay, while for Z, this is the level, and at X is the highest. Okay, since the pressure at point X is the highest. So it pushes the water as the highest level of column P. Okay. Can you follow, can you understand why we draw the level in this way in column P, column Q, and column R? Anyone? Are you clear? Okay, are you drawing same with me? Sama tak, Nicholas? Okay, Nicholas agree. Okay, now you have to explain. Okay, why the water rises at the lowest column in column Q? Why it rises at the lowest level at column Q? Any explanation? Anybody would like to try? Jangan. Anyone? Because higher speed, lowest pressure. Okay, so any other explanation? To try, Nicholas? The thrust push water upward is low. Okay. The rest of you, what do you say? Zihan, Angus, any idea? Eliana? Isian, Sun Xiang? Okay, what happened? So this is how you can give the explanation. Okay, it is quite long, but you can simplify it. Okay. So the first one, water flows at higher speed as Y. Okay, because it has a small diameter. Okay, if you look at the notes up here, this is taken from your textbook. Okay, so when the fluid flows continuously in a pipe, the smaller the diameter of the pipe, the higher the velocity of a fluid. So liquid flow at a higher speed when it passes through a narrow section or smaller diameter pipe. Okay, then what happened? So pressure at Y is the lowest. Okay, this is due to Bernoullis principle. Remember, highest velocity, so lowest pressure. Okay, then atmospheric pressure outside is higher than at Y. So water push to the lowest level at Y. Okay, so this is the reason. Okay, you can explain due to Bernoullis principle. Okay, so done with the explanation. Okay, can we move to the next slide? So far, are you doing good? Can you follow me? Does the temperature change at all? This one not involving temperature change, Kafai. Okay, we are not supplying any heat. So the temperature change is not involved here. Okay. Okay, next students. Okay, next. Okay, this is the second question. Again, we have a venturi tube. Now in this situation, A is flow through tube X and then follow at point 1 and then it went to point Z. And we have again column P, column Q, column R, and we have water down here. Okay. So the first question, at which point is the A is the fastest? Fastest means the air moving with the highest velocity. Okay, which point? X, Y, or Z? according to the diameter of the column X, Y, and Z. So which point the air flow the fastest? Definitely it will be, apa yang same to Terence? What is the same? So this one, which point? Point Y. Do you agree with me? At point Y, the air flow at the fastest speed or highest velocity. Yes, very good, Y. So at which point the water pressure is the lowest? So it will be Y. Sama lah. Oh, I think you will refer to this. Okay, so at these 2 points, okay, the air flow at the fastest and also pressure is the lowest. Okay, again, Bernoullis principle. Velocity inversely proportional to pressure. Okay, now mark the water level in the vertical tube P, Q, and R. Okay, now you can try. Mark the water level. So when the air flows from X to Y and to Z, the water will be rises in each column. Okay, so the water will enter the tube from down here and rises again at a different level. Okay, because we have different pressure at X, at Y, and at Z. Okay, so how do you think the level of water will be? In which column the water rises at the highest level? In which column the water rises at the lowest level? Y have higher. Okay, Nicholas say Y have higher. Okay, then okay, so this is where the water rises at column Y. Okay, and this is where the water rises at column P. And this is where the water rises at column R. Okay. So everyone agree Y, Z, and X. Okay, correct. So this one, the pressure is the lowest. So the water rises up at the highest level. And at X, the pressure is the highest. So the water rises up at the lowest level. Okay, so why the water rises in the vertical tube Q? Again, okay, the same explanation as the previous one. So what happened in this situation, students? Okay, outside here we have what pressure acting outside of the tube? We have atmospheric pressure, right? So atmospheric pressure is acting on the surface of the water. Means there is a pressure difference between in the tube and outside of the tube. And for this one, since the pressure, if you refer to column Q, since the pressure in the tube is the lowest, so the pressure outside means the atmospheric pressure is higher. So it pushes the water at the highest level. So this column will be all filled up with water. While if you look at column P, since the air here has the lowest velocity, mean pressure at column P is the highest. Okay. So pressure is the highest. So the water get in the tube at the lowest level. Okay, are you clear with the explanation for the first and the second question? The first one is the water flowing. Second, the air is flowing through a venturi tube. What is a venturi tube, class? A non-uniform tube. Okay. Or they say, what is another name for non-uniform tube? So it is venturi tube. Okay. So are you done with this? If you are done, okay, let us check on the next part. Okay, now we have, yes, venturi tube. Okay, we have the third situation. Now we have a ping pong ball. Okay, this one, later I can show you, I will show you the demo in the physics lab. Okay, we place a filter tunnel and a ping pong ball down there, and then we open the tap. So you can see that the ping pong ball, what happened? Does it drop or stay there, student? What happened to the ping pong ball? Okay, here the situation given support the ping pong ball in the filter funnel. Support means you hold it first. Okay, then the tap is turned on to allow water to flow through the filter and release the hand which support the ping pong ball. So when you do this, what do you think happened to the ping pong ball? Will it drop or it won't drop as you open the water tap? Any idea? Okay, anyone? What happened to the ping pong ball? Does it drop or not when you open the water tap? Okay, what do you say? No. Okay, how about the others? Will the ping pong drop? The ping pong ball drop or not? Levitate, Terence say. The ball does not fall. Okay, it does not drop. Okay. So what causes the ball to levitate, Terence? Okay, mark with R the region of water flows with higher speed. Okay, student, at which part the water flows at the higher speed? Okay, so you can mark this part. Okay, this is where the water flow at the higher speed. Okay, and this is the region where at the same part, okay, the water flow at the lowest pressure. Okay, the same part R refer to the speed, S refer to the pressure. Okay, then explain what happened to the ping pong ball, why it does not fall, why it stay there, why it is levitate, why it does not drop. Anyone? Okay, any clue? Why it does not fall? So the keyword is lower pressure at upper region. Mana lower pressure at upper region? So what happened, Nicholas? Nicholas say because lower pressure at upper region. Okay, any other idea or any other answer? Pressure different. Okay, that is the keyword. Pressure different. Yes, different in pressure. Different in pressure in which region, student? So this is water flows at the highest speed at R. Okay, this is as we marked earlier. So creating a lower pressure around region R. Okay. Meanwhile, the atmospheric pressure at the bottom is higher. Okay, there is atmospheric pressure acting at the bottom. Okay, and the difference in pressure produce an upward resultant force. So the three arrow down here shows atmospheric pressure is greater than the pressure at the top region on the ping pong ball. So net force acting upward and causes the ping pong ball does not fall. Okay, does this relate to the surface tension of water? Okay, we are not considering surface tension here, Kafai. Okay. Actually, if you use any kind of liquid, it will give you the same result. Okay, you use oil or any other liquid, it will, the ping pong ball will keep there. So the reason is due to pressure difference. Okay. Use mercury. We are not going to use that, Nicholas. Very dangerous. Okay. Okay. So are you done with the explanation? So again, the keyword here, as I mentioned, is the difference in pressure on the top and at the bottom part of the ping pong ball. Okay. Can we move to the next one? Okay. For the others, you can be more active. So we make it this session as a two-way communications. Okay, students. Okay, this is where a high pressure region acting on the ping pong ball. All right. Okay, so number 4. Okay, now we have two balloons. Okay, two balloons are suspended by two threads at a distance of 10 centimeter from one and another. So we place them 10 centimeter apart and we blow through a space between the balloon with the help of a straw. Okay, you boleh tengok di sini lah. There's also a short simulation there. So what happened to the two balloons and why, students? So the first question, what happened to the two balloons? So this is similar as a situation I gave you earlier. So they will move towards each other. Okay, the two balloons move towards each other. Okay, then the next 2 point is the explanation. Why? So you can mention the velocity or the speed of A in the region between the two balloons is high and the pressure is lower compared to the surrounding pressure or the outside pressure. So difference in pressure produce resultant force, which pushes the two balloons towards each other. Okay, this one for the second point, you can write until here only enough. Difference in pressure produce resultant force. Okay, because this one already stated in the first point. So it is okay if you did write them. Okay. So the first one you say what happened to the balloon? It moved towards each other. Okay. And this is the explanation. So velocity of A between is high. So the pressure is lower. And second point, difference in pressure produce resultant force. Okay, you can simplify your answer in that way, right? So the diagram below here I took from your textbook as well. Similar things here, the two ping pong balls suspended when the girl blow in between. You can see both ping pong balls are come into contact. Okay. Okay, are you done with this number 4? Tong Yi, are you done? Jia Yi. Okay, Yu Hui. Wei Xiang, sorry, Yuan Han. Okay, can we move to the next part? Okay. Okay, now what do we have in the next slide? Okay, number 5. Okay, now you are given this situation. Again, a filter funnel and a ping pong ball. Okay, so you are asked to take out the ping pong ball from the filter funnel without using your hand. Okay, we don't want you to take the ping pong ball. Okay, not in that way. So explain what happened to the ping pong ball if you blow A from the bottom, as in diagram A. Okay, so let's say we have one student. He tried to take out the ball by blowing the air from down here. Blow from A. So what do you think will happen? Will the ping pong ball come out in that way? When you blow from A, you blow from down here. Will the ping pong ball come out? Yes or no? Okay, let's say I give you a filter funnel with a ping pong ball inside. I ask you to take out the ping pong ball. So then you blow from A. Do you think you're going to make it? Kafai say no. How about the others? What do you say? Yes or no? I blow from A. Able to make it out, Terrence? No. Okay, why? So the reason, okay, it won't move out. The ball will not move out from the filter funnel. Why? Okay, what happened when you blow air from the bottom? So the velocity of A below the ball will be high. Okay, so in this region, the A flow at the high velocity, which means down here, the pressure is low. Okay. Meanwhile, what happened at the upper part of the ping pong ball? The air here is more calmer, so the pressure is higher. So it means it will push the ping pong ball downwards. Nothing mysterious, Nicholas, only to do with Bernoullis Principle. Okay. So this is the explanation you can give. Velocity of air below is high and pressure produces a low pressure region. So the pressure above the ball is higher. Again, difference in pressure produces downward resultant force. So it's not going to come out in that way. So can you find a way how we can take the ping pong ball out from the filter funnel now? So this method does not work. You cannot blow from A. So where you can blow to take the ball out from the filter funnel? That is the mysterious, Nicholas. Okay, so any idea where it is the best part to blow the air to take the ping pong ball out? So we take it out using our mouth, not our hand. Okay, anybody? Blow but not continuous. Blow where, Nicholas? blow but not terbalik the filter burner. You terbalik guna apa UJ using your hand? Upper, Kafai say blow from upper part. Okay, so what happened when you blow from upper part? Let us see. Either Kafai's answer correct or not. Yes. So this is the correct way to blow the air, student. You blow from the upper part of the filter funnel. Can someone explain what happened now to the pressure and velocity of air above and below the ball? So this is the explanation. Now the ball will move out from the filter funnel. Why? The air above the ball move with a high velocity, so produces low pressure region above the ball. So what happened down here? Air pressure below the ball is higher. So the difference in pressure between the lower and above produces upward resultant force and now pushes the ball out. Okay, so this is the explanation. So the situation is reversed to the first one, A and B. Okay. This one can be a K-part question, hot question as well. Okay. They might give you two figures, A and B. Okay, which one is the best method to take the ping pong ball out from the filter funnel without using your hand? Okay. So we blow again on top of the filter funnel. Okay, so you can write the answer for the explanation for this two situation. If you are done, again, you can type yes in the live chat so we can move to the next part. Okay. Is that a typo, Nicholas? Yes, okay. Okay, students, are you done? So are you clear with this two situation? Okay, so let us move to the next part. So if you miss any point, don't worry, don't be stressed. Later, teacher will show you the PDF for this module 2.6 after tomorrow. Okay, the second part. Okay, now, okay, that is to do with the second learning standard. Okay, to study what is the effect of a lift force acting on an object. So it will cause the object to be lift up. Okay, due to the difference in pressure in the upper and the lower region of the object. Okay, or in between or the outside region of the object. Terence says, so if an aeroplane moves at high velocity, velocity creates a different pressure. Does the atmospheric pressure leave the aeroplane? Okay, in general, yes, Terence, but there's also with the help of the shape of the wing of the aeroplane. We will take a look at that later. Okay, the shape of the wing help much in creating enough lift force to for the aeroplane to fly at a high altitude. Okay. Okay, now this is the most important part, student, the applications of Bernoullis principle in our daily life. Okay, am I answering your question, Terence? I hope so. Okay, so students, there are a few examples. I think there are all 7. Okay, example of applications of Bernoullis. This is the one that relates to your question, Terence. Okay, an aeroplane can fly because its cross-sectional wing has an aerofoil shape which produce a lift force. Okay. So if you look at this shape, student, this is what we call as an aerofoil shape. A-E-R-O-F-O-I-L. Spell it right. Aerofoil shape. Okay. So first you have to draw the stream of the airflow pass on the aerofoil. So this is the upper part of the aerofoil and this is the lower part. And the blue dashed line, it shows the stream of airflow, okay, across the aerofoil. And down here is the short simulation show that the airstream flow across the wing of the aeroplane. Label the region. Second, you have to label the region. So have you draw your airstream flow above and below the aerofoil? You can draw them now according to this diagram. Okay, and label the region with faster airflow and slower airflow. So students, if you look at the shape above, we have a curvy shape. Okay, a curved shape. So the air here flow at the higher velocity. And below the aerofoil, it has about a plane shape, okay, a straight line. So here, the air is more calmer, lebih tenang, mean the air here flow with the low velocity. So which means that the pressure down here is higher. So the pressure above is lower, okay. So you label the region with higher pressure and lower pressure. Okay, then indicates direction and label the force acting on the aerofoil. So due to the pressure difference above and below the aerofoil, since below here pressure is higher, above pressure is lower, so the net force is acting upwards, okay, and creating a lift force on the aeroplane. Yes, okay. So have you done with your drawing? Draw the stream, the first one, label the region, faster airflow. So here you can label V high, okay? Here V low, V for velocity. And third, the pressure, here you can label pressure is P, capital P. P low, down here, P high. Okay, you can use the upward arrow as well, like this. So this one V high, so the pressure is low. Okay. Meanwhile, for down here, the speed of A is lower, so its pressure is higher. Okay. So the net force is acting upwards. This one, lift force, F, labeled with F, with the red arrow, acting upwards. Okay, very good. Okay, so again, the shape is aerofoil shape. Okay, next. Okay, so this is a short demo how a plane make a takeoff. Okay, so the first one, how to explain, we can explain through Bernoullis principle. Okay, explain how the uplift force is produced to help the plane take off. Okay, for this kind of question, if it come out in the section B or section C, mean essay carry 4 marks. Okay, working principle of lifting force produced on an aeroplane, okay, 4 marks. So the first mark, okay, you can explain through Bernoullis principle. So according to Bernoullis principle, student, it say the higher air velocity at the top section of the airfoil, a shape wing produce region of low pressure, while the low air velocity at the bottom section produce a region of high pressure. Okay, this one you can simplify. Okay, boleh ringkaskan saja. Okay, according to Bernoullis principle, higher air velocity on top produce low pressure region. Okay, while lower air velocity at the bottom produce a high pressure region. So second point, difference in pressure produces lift force. Okay, the second point. And a part of that, the lift force is strengthened by the angle of attack. This is another thing. At certain angle of attack, what is mean by angle of attack? Angle of attack means the position of the wing, okay, from the horizontal axis, as you can see in this figure, students. Okay, this is that we call as the angle of attack. Okay, if you are used to be on board, kalau yang biasa naik kapal terbang, you will see that the wing of the aeroplane changes in size. Not changes in size, I mean changes in direction. Okay, when it is about to take off or when it's about to land. So it means it changes the angle between the wing and its horizontal axis. Okay, So this angle of attack exerts another force, meaning it gives an additional lift force to the aeroplane. Okay, and according to Newton's third law, a reaction force acting on the wing, adding a lift force. So, due to the position of angle of attack, it added another lifting force, okay, to the aeroplane. So, making the total lift force is greater. So, it is greater than the weight, so they can fly off. Okay. If there is no air, can the plane still be able to take off? No air. No air macam mana? Kafai said, if there is no air, can the plane still be able? So can you imagine what happened in outer space? Can you imagine how the plane will move in the outer space? Definitely no, Kafai. Okay. The situation will be different. Okay. Correct first. Okay, so no air means no air flowing, so no lifting is produced. As simple as that. Okay. So that's why if you want to launch a satellite in the outer space, okay, we don't launch the satellite in this way. We launch it in the vertical direction with a very high thrust producing from the combustion of the fuel inside. Okay, so it goes straight up, and so it then it against gravity. So when it reaches the outer space, so there it will follow the if you follow gravitation before this, so as it reach the escape velocity, then it can go to the outer space macam tu. But for this aeroplane, since it is only operating in the Earth atmosphere, so it requires air for the takeoff. Dia mesti ada udara lah. Okay. So are you done with this explanation, students? It is quite long, but you can just write the blue wording. Yang biru saja itu the keyword. Okay. So I hope I'm answering your question, Kafai, am I? Correct first stage. Okay, students. Next. Okay. So the first application is on aerofoil wings of an aeroplane. Okay. Second, we have insecticide sprayer. Okay, insecticide sprayer. Okay, this is the structure of an insecticide sprayer. Okay, what happened at the narrow opening when the piston is pushed into the cylinder, students? So this is where the piston, okay, this is the cylinder. It looks like a shrimp. Okay, and this is the tank, the insecticide tank, and this is the nozzle or the narrow opening. So what do you think happened at this narrow opening when we push the piston inwards? Okay, anything come up from the nozzle? What happened there? The air there move out with high velocity, creating a region of low pressure. So this is what happened. You push here mean the air move and come up from this narrow opening. Since the size is narrow means small in diameter if you refer back to the venturi tube earlier. So the air here will move with a high speed, okay, or high velocity. So creating a low pressure region at this nozzle. Okay. Second, how does the insecticide rise through the metal tube? Okay, this is the metal tube. Okay. The column in it called the metal tube. How does the insecticide from the tank able to rise up through the metal tube? Students, what happened? How? Okay. So in this tank, high atmospheric pressure push the insecticide through the metal tube. Okay. High atmospheric pressure inside the tank push the liquid so it comes out. Okay, it comes up through the metal tube. Okay, and finally, the third question, how does the fine spray produce? If you look at the simulation, it spray the liquid with a fine spray, semburan yang halus. Okay, how this fine spray can be produced? Anyone? Okay, you can relate to the velocity of A there at the nozzle. So how we explain the insecticide which rise through the metal tube will push by the high velocity A from the narrow opening as a fine spray. Okay. Yes, due to high speed, Nicholas. This is not only occur in insecticide spray, it applies in all kind of spray, including perfume. If you are using perfume sprayer, so this is the mechanism how the perfume can come out with the fine spray, okay, from its nozzle. Okay. Okay, are you done with the second application, insecticide sprayer, students? Now is 11 past 10. Okay, I think we can finish with the application. And tomorrow we can do a question, a problem solving involving Bernoullis Principle. Okay, can we move to the next part? Yes. Sampai pukul berapa? 11 past 30. 11.30 Nicholas. From 10 to 11:30. Okay. Or you want to make it until 1? I don't think so. Okay. Okay, next. Okay, this is the third application. Okay, Nola. Okay, I also need to go to GH after this. Okay. Okay, Bunsen burner, the third application, student. You are familiar with Bunsen burner, right? You use a lot, especially in chemistry lab. Okay, Bunsen burner. Sinway, hungry? Belum sarapan ke, Sinway? Okay. So student, this is the structure of our Bunsen burner. It has a hole there with a narrow outlet and the gas supply from this part. Okay. Mark with X, the region where gas flow with high speed. Okay, where is the part X? The gas flow with the high speed, student. Okay, of course, it will be at the, yes, at the narrow outlet. So here, okay, the air or the gas supply flow with a high speed when it comes up from the narrow outlet. Okay, what happened at the jet when a Bunsen burner is connected to a gas supply? So this is what happened at the jet. So a high velocity gas move out through the jet. So this is the jet, okay, the narrow outlet. We also call it as a jet. High velocity gas move out through the jet to produce low pressure region. Okay, and due to that, high atmospheric pressure from outside push the air into the hole. So what happened when air mix with the gas? When air from outside meet with the gas, so combustion occur. Okay, combustion occur and produces flame on top of the burner. Okay, how a blue flame is produced? Blue flame. Okay, now here you can see a red flame. You learn in chemistry, right? What is the difference between blue flame and red flame? It is due to complete or incomplete combustion. Okay, so blue flame means complete combustion. So air mixed with the gas to produce a complete combustion, which produces the blue flame. So this is what happened when you open the when you open the air hole. Okay, and when you close the air hole, you will get a red flame. Am I right? If you open the air hole, complete combustion occur. So you will get a blue flame. Do you remember how to use a Bunsen burner? Betul kan? You buka lubang, nanti you dapat api biru. And when you open the air hole, complete combustion occur, the flame will be blue. And when you close the airflow, you close the air hole, the combustion will be incomplete. Why incomplete? Because less oxygen from outside enter. So the combustion is incomplete, producing red flame. Okay. So Bunsen burner third application applies Bernoullis principle involving speed and pressure of moving fluid. Okay. Now, the fourth application. Okay, curveball. Curveball. Okay, for those who are playing rugby or playing baseball or softball. Okay, so this is related to those sports. Okay, figure A shows a moving ball that is not spinning, whereas figure B shows a spinning ball that is not moving forward. Okay, did you get the two situations? This is the airflow for both situations. Magnus effect. Yeah, Magnus effect. Okay, good parents. Okay, so what happened in diagram A, students? In diagram A, it say that the ball is moving, but it is not spinning, mean it is moving in a stagnant way. Okay, so what happened in diagram A? The ball is moving to the right, it moves to the left. Yeah, who's that? Towin.
Yes, teacher, yes. Hello, teacher.
Yeah,
Hello. Hello.
are you at IPD now?
Yes, Digo. Kami kena tangkap ah.
Okay,
Kami kena
I
tangkap
saw
ah.
Yeah, I saw your picture this morning. Cikgu Lizawati post in our Telegram group. Okay, good luck for you there. You today. Okay, have a good training. Okay. Okay. Cadet police boleh. Okay, then the ball moving to the right, so S3 move to the left, opposite. So you can draw this is show the direction of S3. It is opposite to the direction of the moving ball. And in case B, in case B, what happened? In diagram B, the ball is spinning clockwise. So the ball is spinning in a clockwise rotation. So at the bottom, A stream move at the left, means same direction. And on the top, the A stream move to the right in opposite direction. Okay? If you draw the S stream macam ni lah bawah ni, this is the S stream. Okay? And above, this is the S stream. Okay, for A also the same. Above, this is the direction of A stream, and down here, this is the direction of A stream. So for this one, the ball continue moving in a straight line when it is not spinning. Okay, when it's not spinning, it is continue moving in a straight line. Okay, as there is no pressure difference above and below. Okay, the pressure is the same. Okay, but for this one, what happens, student? Okay, now the ball is spinning in this direction. Okay, it is moving and spinning at the same time. So what happened on top? On top, the direction of the ball is opposite or against the direction of the airflow. Okay, and below, the direction is the same. Okay, so what do you think happened to this ball? That's why it is spinning but not moving forward. Mean it is keep floating there. Okay, it's floating there, not moving to the front. Okay, then what happened next? Okay, so kita tengok yang ini. Okay, another ball moving in a spinning direction through A. Okay, so you can see now this is the direction of the ball. It's spin in a clockwise direction. Okay, and this is the A stream above, and this is the A stream below. Okay, so above, what do you say the direction of the S stream and the direction of the ball? Are they same or opposite? Above. Direction of ball and direction of S stream above. Opposite or same direction? From the arrow I drew just now. Opposite or same direction, students? Direction of spinning ball is clockwise, and this is the direction of airflow. So above, opposite or same direction? The air and the ball. Above, this is the direction of the ball. Down here, this is the direction of the ball. Yes, above is opposite, Sinway. Thank you for your response. How about the lower part? The direction of the ball and the direction of the wind, it is equal, right? It is the same direction. Both directed to the left. Here, upward, ball direction to the right, but the airflow directed to the left, so opposite direction. So what will happen then? and how the ball will move. Okay, so we can say like this. The bottom side of the ball has a high velocity. Why? Because both extreme combine as the flow of extreme in the same direction of this. So here as the direction of the ball and the direction of the A is the same, so it creates a high velocity A down here. So down here A move with the high velocity. Meanwhile, what happened at the top? At the top side has a low velocity since the direction of A stream is opposite to the direction of spinning of the ball. Okay. And then what happened? According to Bernoullis Principle, as the region with high velocity produce low pressure. So down here, high velocity. So the pressure is low. Okay. Meanwhile, up here, the velocity is low. So pressure is high. So again, you can see there is a pressure difference on top and at the bottom of the ball. So this will cause us a resultant force or a net force acting downwards. Okay. So what happened? Now the ball will move in a curved line. Dia akan gerak macam inilah, in a curved direction. It changes the direction of motion of the ball. Okay, it will move in a curved path, not in a straight path anymore. Okay. So this is actually what's related to the two figures I gave you earlier. Later we will see how they are created a ball moving in a curved direction. Okay. So are you done with this one, Sudah ke? In this one, you have to fill in the blank spaces only, right? With the blue wording, if I'm not mistaken. Okay. Yeah, better colors curve kit. It is called the banana kit, Terence. Okay. Okay, let's check. What do we have?
Carlos set up for a 35-meter free kick.
Can you hear the sound from this video?
Carlos decided to.
Can you hear the sound from this video? Okay.
In 1997, in a game between France and Brazil, a young Brazilian player named Roberto Carlos set up for a 35-meter free kick. With no direct line to the goal, Carlos decided to attempt the seemingly impossible. His kick sent the ball flying wide of the players, but just before going out of bounds, it hooked to the left and soared into the goal. According to Newton's first law of motion, an object will move in the same direction and velocity until a force is applied on it. When Carlos kicked the ball, he gave it direction and velocity. But what force made the ball swerve and score one of the most magnificent goals in the history of the sport? The trick was in the spin. Carlos placed his kick at the lower right corner of the ball, sending it high and to the right, but also rotating around its axis. The ball started its flight in an apparently direct route, with air flowing on both sides and slowing it down. On one side, the air moved in the opposite direction to the ball's spin, causing increased pressure, while on the other side, the air moved in the same direction as the spin, creating an area of lower pressure. That difference made the ball curve towards the lower pressure zone. This phenomenon is called the Magnus effect. This type of kick, often referred to as a banana kick, is attempted regularly, and it is one of the elements that makes the beautiful game beautiful. But curving the ball with the precision needed to both bend around the wall and back into the goal is difficult. Too high and it soars over the goal. Too low and it hits the ground before curving. Too wide and it never reaches the goal. Not wide enough and the defenders intercept it. Too slow and it hooks too early or not at all. Too fast and it hooks too late. The same physics make it possible to score another apparently impossible goal, an unassisted corner kick. The Magnus effect was first documented by Sir Isaac Newton after he noticed it while playing a game of tennis back in 1670. It also applies to golf balls, frisbees, and baseballs. In every case, the same thing happens. The ball's spin creates a pressure differential in the surrounding airflow that curves it in the direction of the spin. And here's a question. Could you theoretically kick a ball hard enough to make it boomerang all the way around back to you? Sadly, no. Even if the ball didn't disintegrate on impact or hit any obstacles, as the air slowed it, the angle of its deflection would increase, causing it to spiral into smaller and smaller circles until finally stopping. And just to get that spiral, you'd have to make the ball spin over 15 times faster than Carlos's immortal kick. So good luck with that.
So this is the Magnus effect as written by Terence, or the banana kick. So I think in your next PJ session, boys, you can try to apply this Magnus effect. See you can make the corner kick or not. Boleh cuba nanti. Jangan main badminton sajalah sepanjang masa. Okay. So very good to try on your own. See, you can create the Magnus effect or not. So are you able to apply Bernoullis principle or not? Okay, so try on the next PJ session. Okay. Okay, so number 5, the sailboat. Okay, sailboat. So this diagram shows the sailboat move against the wind. Okay. So compare the speed of A stream at A and B. Okay, this is the figure relates to this question. We have A and we have this is B. Okay, this is the shape of the sail. Layar itu sail lah. Okay, so which one do you think the air move at the high speed, at A or at B, according to this shape shows now? Okay, in B we have a curve shape. This is the aerofoil, and at here we have the plane shape there. So which part do you think the A move at the higher speed? Compare the speed of A stream at A and at B. So what do you say, students? At which part the A flows at the higher speed and which part it flows at the lower speed? B higher. Nicholas say B higher. Do you agree with Nicholas, everyone? Okay, so B greater than A, yes. So comparison, so we say speed in B is higher than speed in A. Okay, compare the air pressure now at point A and point B. Which one higher pressure, which one lower pressure? So when talking about pressure, it is opposite to the air speed. So B less than A, okay, or vice versa. Air pressure at B lower compared to air pressure at A. So now student mark with F the direction of resultant force acting on the sail. So in which direction the sail will move to? So you mark. So since A here the pressure is higher, so B pressure is lower. So from the Magnus effect we saw just now from the video, okay, so force move from higher pressure to a low pressure region. Okay, and last question, mark with X the movement of the direction of the sailboat. So this is where the sailboat move at. Okay, it will move forward against the wind. So if the sailboat wants to move forward against the wind, so it has to be from the help by the sail daripada layar ini. Okay, then okay, this is how the explanation given. Explain how the sailboat can move forward against the wind. Again, you can explain due to pressure different in between of part A and part B. So A move with a high velocity at B, creating low pressure area, which means high pressure at A. So difference in pressure produces resultant force. So sailboat move forwards against the wind. It's a very simple explanation, okay, as we did earlier on the ping pong ball, on the paper, and on the can. Why don't the sailboat move in the direction of the resultant force? Kenapa? Maksudnya dia gerak ke sana. Okay. If you look at the shape, okay, the wind will actually the sail will help the sailboat to moving in a straight or in a forward direction, okay, which is against the wind. Only the shape in this only the sail, you have to make it in this position. So students, if you want to change the direction, let's say you want to make the boat, moving in that direction. So the position of the sail ini has to be changes. So that's why if you follow this spot in the television, you can see that the sailor, they changes the position of their sail every time. Okay, either they want to move forward, or they want to move to the right, or they want to move to the left. So in this position, Nicholas, okay, the force just now we draw is acting on the sail. Okay, mean it pushes the sail in this direction, but the boat is keep moving forward. Okay, unless boat ini dia in this direction, unless the boat ini in that direction, so it will move into the right. Okay, like that. Okay, or the boat is now in this direction. Okay, so they adjust the sail so it will continue move in this direction. If they want to make a corner, make a turn, then the sail have to be adjusted from time to time. Okay, so to create an angle so they can make a turn or a curve. Yeah, on the sail, not on the boat. Yes, the resultant force, apply on the sail. Correct. Okay, it's a very good question though. Okay, then students, okay, that is this is the last two application. Okay, last two application. It shows the roof of a house being lifted by strong winds. Okay, explain how the roof is lifted. So the situation is just about the same, and this is a past year SPM question. Soalan SPM tahun-tahun lepas lah. Okay, so you always mention about the air velocity on top and below of the object, and you tell about the pressure. And the third point, always the pressure difference, and finally produce a resultant force or net force acting, which causes the roof to be lifted. Okay, so air move at the high speed above the roof, so create a low pressure region above. Okay, meanwhile, below the roof or inside the house, it is a high pressure since the air there is calmer. So due to the difference in pressure, upward resultant force produces and causes the lift to be applied over or lifted. Okay. So now you understand, okay, this phenomena is related to Bernoullis principle. It is a disaster. Okay. One negative effect from Bernoullis principle. Normally happen during a thunderstorm. Okay. So now it's 11 past 32. Okay. Okay, you want to continue with number 7 or we continue this for tomorrow? Okay, application number 7 and a few example of exercises or question relate to Bernoullis principle. Yeah, we can overcome this disaster. Yes, correct. Esok lah. Okay, Yujia. Okay, so students, I think that's all for today. So we have discussed the third learning standard on Bernoullis principle. So tomorrow we will come back on the same time at 10 a.m. to 11:30 a.m. with the final application number 7, and also the most important part, problem solving on Bernoullis principle. Agree. Okay, I understand your situation. Okay, okay. But so far, students, thank you very much for being here. I really appreciate your effort. So I hope you are doing fine with Bernoullis principle so far. So you can try the question first and we check for the answer tomorrow. Okay, thank you very much. And sorry for the technical error at the beginning of this lesson. Okay, Vida, bye-bye and see you tomorrow. Thank you, everyone.